Hello and welcome to the MathOS channel. In this video I'll talk about the Fibonacci sequence. And there you should say, again Fibonacci. What do they all have with it? There are literally tons of videos on YouTube about that story. But believe me, what I'm going to tell you about that sequence is generally unknown, and you're not likely to find it elsewhere on YouTube. First of all, I need about 2 minutes to remind you exactly what we're talking about. And let's start with the definition. The Fibonacci sequence is defined by its first terms 0 and 1, together with this recurrence relation. In other words, each term is the sum of the two previous ones. This way, we can easily compute the first values. This formula is a special case of what mathematicians call a homogeneous second-order linear recurrence relation with constant coefficients. For such a sequence, we've got a recipe that enables us to compute directly any term. By applying this recipe to the Fibonacci sequence, we get the following formula, also known as the Binet formula, which involves the golden ratio, denoted by phi, and its conjugate, the number -1/phi. Now, the asymptotic behavior of f sub n as n goes to infinity is straightforward. Since 1 minus square root of 5 over 2 is strictly comprised between -1 and 1, its powers converge to 0, while the powers of phi diverge towards infinity. Therefore, f sub n is equivalent to phi to the nth power divided by square root of 5. Now here is something new. If we develop those two expressions using the binomial theorem, we obtain f sub n equals to a sub n minus b sub n divided by 2 to the nth power multiplied by a square root of 5, with a sub n and b sub n respectively given by those formulas. By subtracting those powers, the terms with even indices vanish, and here is what's left. Thus, a sub n minus b sub n is equal to 2 times square root of 5 multiplied by the sum from q equals 0 to flow of n minus 1 over 2 of n choose 2q plus 1 times 5 to the q. And finally, here is a new expression for f sub n. Now I'd like to ask you something. We know that f sub n is a positive integer. This is quite obvious from the definition, but frankly, the fact that this expression represents an integer is not clear at all. A positive rational number, of course, but an integer. If you know some way to prove it in a straight fashion, which means not simply by doing the previous calculations in reverse order, but rather by using some arithmetical argument, then you have to leave me a comment. Let's move to another question. Is it possible to find a first-order recurrence relation which defines the Fibonacci sequence? If I may rephrase, what sort of function could we find which maps f sub n to f sub n plus 1 for every value of n? After careful inspection, we can see that there's something wrong in that question. Indeed, we would have u of f sub 2 equals to f sub 3, and in the same time u of f sub 1 equals to f sub 2, which is quite impossible. So we have to add some water to the wine. Let's look for a function u such that this relation holds starting at index 2. This should remove the issue, since the f sub n are all distinct when n is larger than or equal to 2. Would you like to have some time to think about it? You may pause the video now, and we'll resume right after that. We may find inspiration into one of the previous observations. We have noticed that 1 minus square root of 5 over 2 to the n tends to 0, while 1 plus square root of 5 over 2 to the n diverges to infinity. Now consider the function which maps every irrational number x to the integer closest to it. Restricting our function to the set of irrational numbers is convenient, because the integer closest to x is undefined when x is the rational number of the form q plus 1/2, where q is an integer. And this is not a limitation, since we're going to apply this function only to irrational numbers, as you will see. I will let you do the necessary calculations and prove that if we denote by psi the number -1/phi, we have phi times f sub n equals to 1 over square root of 5 multiplied by, in parentheses, phi to the n plus 1 minus psi to the n plus 1 plus psi to the n times psi minus phi, which simplifies to f sub n plus 1 minus psi to the n, because this difference, psi minus phi, is barely negative square root of 5. As a consequence, the gap between f sub n plus 1 and phi times f sub n is less than 1/2 for each integer n greater than 1. And here is finally the first order recurrence relation we were looking for. Starting with index 2, each term in the Fibonacci sequence is the integer closest to the product of the golden ratio by the previous term. Did you know that? Let's move to another context. There are plenty of nice-looking formulas leading to explicit expressions for sums involving binomial coefficients. Here is the famous Pascal triangle, an infinite array which contains the values of all binomial coefficients. If this looks unfamiliar to you, I suggest you to read a post on my blog math-os, which introduces all the necessary stuff. But you should be warned, all of this is written in French. Anyway, you'll find the link in the description below. If you add all the terms on the nth row, you'll get 2 to the nth power. This is a well-known result. If you pick a term somewhere on the diagonal and add to it the ones below it, down to some level, you'll find the binomial coefficient located on the right and on the next row. This is an easy consequence of the Pascal formula. I'll spare you the details. Now look at this. If you add the binomial coefficient along any ascending diagonal, then here's what you get. 1, 2, 3, 5, 8, 13, 21, etc. As you can see, those calculations produce the Fibonacci numbers. In symbolic notations, the sum from k equals 0 to floor of n over 2 of n minus k choose k is equal to f sub n plus 1. It's a very good exercise to prove this in full generality. Finally, let's look carefully to the first Fibonacci numbers. Is there anything that surprises you? Yes, those numbers are perfect squares. Are there any others? And if so, how many? This question can be addressed experimentally. We can consider things in at least 2 ways. First, enumerate the Fibonacci numbers in ascending order and look for perfect squares. Or, enumerate the perfect squares in ascending order and look for Fibonacci numbers. Clearly, the first way is the better one, since the Fibonacci sequence grows by far much faster than the perfect square sequence. No contest. In my Happy New Year video, which you can access using a link given in the description, I propose a few lines of Python code to decide whether a positive integer is a perfect square or not. You can go back to it and do the programming by yourself. And if you do so, you'll notice that except for 1, 0, and 144, there are no other perfect squares among the Fibonacci numbers of index less than 2000. And f sub 2000 is quite a huge number. Of course, this doesn't prove anything, and it could be that there are other perfect squares later on. But we can formulate the conjecture that there aren't any. And this is in fact a theorem. which has been proved by John Cohn in 1964. You will find a link to its proof in the comments down below. Recently, in 2004, it has been proved by Bugeaud, Mignot, and Sixek that the only perfect powers in the Fibonacci sequence are 0, 1, 8, and 144. The proof is far from being simple. One could also ask, what are the Fibonacci numbers which are also prime numbers? This question seems to be out of reach. It's not even known if there are infinitely many such integers. In January 2022, the largest known such integer is f sub 148,091, a monster whose decimal expansion has more than 30,000 digits. Well, that's it for today. I hope that you enjoyed this video. I would appreciate to read your comments, and I hope that we'll meet again very soon on this channel.